Okay, today we're going to be working what we call applied optimization problems. What we're trying to do here to optimize, we're trying to find maximum points, minimum points. Production-wise, you see this a lot in the industry. You're trying to maximize production. You're trying to pretty much stretch your dollar as far as it'll go. Trying to minimize material that you use. If you're trying to construct something, you want to construct something with the minimum amount of material. You're wanting to get the maximum volume, maximum area, make it as big as possible with as little material as possible. So that's what we're doing today, is you're seeing some of the application problems of all of this calculus stuff. Reminder that maximums and minimums occur. Critical points occur anywhere your derivative is equal to 0, or we know with like this type function, anywhere your derivative could be undefined would be a possible maximum or minimum point. So that's what we're going to do. We're going to try to set up different functions, relationships among what we're given, and we're going to try to find the points of maximum or minimum, really whatever we're looking for. Okay, we're going to start out with an easier problem. Well, we've got a rectangle that has an area of 9, and we want the smallest perimeter possible, or the smallest dimensions possible. First thing on these problems, well, you can start out by drawing pictures just to where you get an idea of what you're looking for. You've got a rectangle with an area of 9. You want to somehow figure out which rectangle is going to have the smallest perimeter possible if it's got this area. We don't know length or width, but we do know that to find area of a rectangle, you have to multiply length times width. So what you're going to do, again, draw a picture to kind of give you an idea, and then try to define. Here's the key point, and you might want to star this, make sure that you know this. Try to use as few of variables as possible. Like here, I'm going to let one of my side lengths be x. Don't let the other side length be y. If at all possible, try to define as much stuff with a single variable. And that's what we're going to do here. Is we've got a side length of x. We've got the other side. Well, I know in order to you can start out calling it whatever you want to. I'm going to call it w just to show you something, because sometimes I have to do this. I know that when I multiply these two things, x times w, it's going to give me that area that I'm talking about. But I would really, instead of defining this in terms of w, I'd really like to define it with x's. So I can go up here and actually solve this little equation, move the x over, and I know that w is equal to 9 divided by x. So instead of defining this in terms of w, let's try to define it in terms of x. So I've got this rectangle now that's got a side length of x and another side length of 9 divided by x, and you can check that. The area should be 9. If you multiply x times 9 over x, x's cancel, leaves you with 9. So it checks out. So here's my rectangle, and I want to somehow, it says, I want the smallest perimeter possible. I want to somehow minimize perimeter. Well, first off, let's write a function for perimeter. I know that the perimeter is what you get when you add up all four sides. So I have here, this is x, this is also 9 over x. So I have x plus x, which is 2x, plus 9 over x plus 9 over x, which would be 18 over x. You've got common denominators there. We're about to try to minimize or maximize perimeter. So a reminder that maximums and minimums occur of a function anywhere your derivative is equal to 0. Okay, one thing I noticed, we're about to find the derivative of this, so go ahead and take this 18 over x, and let's write this perimeter as 2x plus 18x to the negative 1, which makes it so much easier to find the derivative of. So here we go, we're ready now. We find maximum and minimums anywhere that we have undefined or 0 derivatives, anywhere our slope's equal to 0. Before we do that, though, I should have done this before. We have to be very careful of our domain. The things that x can and can't be, because if we find a maximum, hey, I think I have a maximum at x equals 25 or x equals a million or something like that. We've got to make sure that that's a value that x could possibly be. And I do know this, since x is a side length, the domain, I do know that x has to be greater than 0. It's not greater than or equal to. Now the question is, could x be something like 100? Can I do 9 divided by 100? Sure. If x is 100, then you got 9 100ths, and I guess x could be a million here. If x is a million, then you got 9 divided by a million, which is a really skinny side, but it's possible. Okay, if this is a million and this is 9 over a million, you multiply the two, you still get an area of 9. So this is my only domain restriction. We've got to make sure that x is a positive number. X can't be -3 because it's a side length. So here, back to it. Minimize perimeter. Let's go ahead and find the derivative. Derivative of 2x is 2. The derivative of 18x to the -1, bring the -1 down front and multiply, is -18x to the -2. We're going to rewrite that as, let's go ahead and put this stuff first, -18 over x squared plus 2. So that's the function that I'm going to try to find a zero derivative, or anywhere it's undefined, because again, my critical values occur anywhere a function's undefined, which goes to show you also that that's another important reason to do this. I know that my function is undefined at 0, but it's not a critical value because x can't be 0. Okay, I'm not going to have a maximum or minimum at 0 because x can't be it. All values of x has to be bigger than 0. You plug in a 0 here and nothing happens. You've got an undefined function. So we don't have anywhere where the function is undefined because of our domain. But we will have places where my function is equal to 0. That's where we're looking to solve now. That's going to be my critical value. Set it up equal to, derivatives equal to 0. Let's move our 2 over and our x squared at the same time. I got -18 equals, when the 2 comes over it becomes -2. I'll end up multiplying by x squared. That'll be -2x squared. Divide now by -2 and you get 9 as x squared. Square root both sides, you get x is, you don't have to worry about positive -3 again because of this. X is 3. That's my critical value. X equals 3. Now, most of the ones that they're going to give you, and I'm going to do it here, most of the ones that they're going to give you, they're going to use what we used last section. This is a critical value. Something's happening here. I want to see, is this possibly a maximum or a minimum here? And here's how you do it. Go ahead and find the second derivative. You could look at the graph and do this exact same thing. The way we're going to do it today, we're going to find the second derivative. Let's take it from here. The derivative of 2 is 0. The derivative of -18, x to the -2, bring down the -2, gives you 36x to the -3, which is 36 over x to the 3rd. There's your second derivative. Here's the only reason I have to find the second derivative. Plug the critical value in. You get 36 over 27, which is a positive number. What that tells you is, reminder, a second derivative tells you concavity. It tells you whether your function is concave down or whether it's concave up. If you get a positive value, it's concave up. If you get a negative value there, it's concave down. So at your value, at your possible critical value of x equals 3, you have a function which is concave up at that value, which is a critical value. And if it's concave up at a critical value, that must mean that you have a minimum at that critical value, which is what we were looking for. So at x equals 3, which we go back to our original drawing, I like to do this. When x is 3, you have 3 here, and you have 9 divided by 3, which is also 3 here. You've just minimized the perimeter. They're also going to ask you on your homework, find the value of a side that minimizes the perimeter, and then actually find the perimeter. What's the smallest perimeter that this area of 9 could have? That'd be, this is 3, so the perimeter would be 12. So the side length that minimizes, and you can try different ones now. You can try, well, what if this was 2 and this was 2? You'd have 2 and 2 is 4. That'd be 4.5 and 4.5, which is 9. 4 and 9 is 13. That's a little bit bigger. This is the smallest perimeter that you can possibly have if you have an area of 9. Okay, on the next one, it says, find the dimensions of an open rectangular box of maximum volume that can be made from a sheet of cardboard that's 13 inches by 8 inches by cutting congruent squares from the corners. So see if you can picture this. We're going to cut little bitty squares, congruent, same size, has to be in order to do this. We're going to cut little squares out of the corners of this rectangular piece of cardboard. We don't know how big they are, but since they are squares, they'll be X by X squares. Once we cut these off, we're going to fold this up, we're going to fold this up, all the way around. It's going to form a box, okay, a rectangular prism. And we want to know how big of corners should we cut out to where when we fold this box up, we get the biggest box possible. And again, you see, when I first started out, we're talking about manufacturing, why this would be valuable. Why would this be something good to know? We want the box that's going to hold the most amount of material. Or if we're a cereal company, obviously we want the box that will hold the least amount of cereal, but it looks like it's going to hold the most. To where they're going to get about 2 bowls of cereal out of it, and then they're going to have to go back to Walmart and buy another one. So here we go. Here's how we're going to do it. First off, let's figure out what the volume of this box is, and see if this makes sense. If the whole side is 13, if you can try to picture the box after, let me see if I can draw it. The box after you cut those corners out, it's going to look kind of like this. Okay, you've cut this out here. You've folded this up for a side. That side is no longer 13. Okay, because you cut out whatever this length is and whatever this length is, and that's going to be the length of whatever this side is, which would be the full 13 that you had before, but you cut out an X here and you cut out an X here. So the width of this side is going to be 13 minus 2x. The width of this side, well, it was 8 until you cut these little chunks out, and now this is all you're folding up for a side, is just this portion. So you cut an X out here and an X out here. The width of this side will be 8 minus 2x. And then once you fold it up, the height of your box, anybody know what that is? The height will be X. So this is 13 minus 2x, this is 8 minus 2x, and the height of the box is x. We want to maximize volume. We want the volume that's going to be largest. How big of an x do we need to maximize volume? So first off, let's actually find a formula for volume. Length times width times height, or the area of the base times the height. So that'd be x times 8 minus 2x times 13 minus 2x. That's the formula for volume. And here's my thing. You can leave it like it is and then find the derivative, because we want to find where's the highest volume. If you leave it like it is and find the derivative of this, you're going to have to use the product rule twice in the same problem. It's going to be terrible. My suggestion, use your basic algebra and go ahead and FOIL that out. It's going to make the problem much, much easier, because you're going to end up with just like a polynomial. So let's go ahead and do that. So volume is equal to, leave the x. It's going to be easy to just distribute that at the end. You have 8 times 13, which is 104. 8 times negative 2, which is negative 16x. Negative 2x times 13, which is a negative 26x. And negative 2 and negative 2, which is a positive 4x squared. Next, I'm going to distribute that x, and as I do that, this is negative 42x. As I distribute the x, I'm actually going to put these in order as well. I'm going to put my 4x squared first. X times 4x squared will be 4x to the third. Negative 42x times x will be negative 42x squared, and 104 times x will be plus 104x. So here's my formula for volume. That's what I'm trying to maximize. I'm trying to figure out what is the largest value of x that I could possibly have. Something I also forgot how to do. Something else I forgot to do is I need to define my domain restrictions. What are some values that x could be, and what can x not be? Let's point out that obviously x can't be negative, because how in the world can you have a negative height? X can't be 0. You can't have a 0 height. So let's say that x must be positive, or has to be greater than 0, and has to be less than. Okay, look at here. If x were 4 here, 8 minus 8 is 0. That'd mean you'd have a 0 width. So there's no way possible that x could be 4. There's no way, well, here x can't be 6.5, but that's not going to come into play as long as we fix this. So x has to be somewhere between 0 and 4, not including 0, not including 4. That's my domain. That's the only values. That's the short interval where I've got to try to find a maximum volume here. Is somewhere between 0 and 4. So what is the maximum volume that I could occur, or that can occur in this height here? Let's find out. So in order to find that maximum, again, find v prime. And it's a simple polynomial now. Move the 3 down front, multiply, take 1 away. Same thing here, negative 84x. And 1 times 104 is a positive 104. So there's your v prime. Anywhere it's undefined or anywhere it's 0 is where your critical values occur. This cannot be undefined. There's no value that it's no fractions, there's no square roots, there's no tangents, there's no anything like that to force undefined here. So all we're working on, I'd reduce this, divide everything by 4, gives me a 3x squared negative 21x plus 26. 0 divided by 4 is also 0. That's legal. That's the reason it's legal, is because I did 0 divided by 4 as well. This is a quadratic equation. We've got to solve it equal to 0, so it goes back to that same. You can try to factor it. Real world, nothing factors. You know, we spend so much time working on factoring, but if you're talking about a real world application, this ain't going to factor. You're going to have a decimal value that's going to give this an answer of 0. So real world, you're going to have to use quadratic formula. Negative b plus minus the square root. I always like to do this over to the side. B squared. I'm going to go ahead and do the whole thing. B squared minus 4 times a is 3 times c is 26. Gives me 129. Over 2a is 6. Remember your domain restrictions. I don't know that you're going to get 2 different answers here. You might just get one, because sometimes you'll have like 21 minus. If you do a square root there and you get a negative, x can't be negative. You can throw that answer out. This one, well, you know what, I can already look ahead and I know why, but this one will give you 2 answers. So we got 21 plus root 129. Let's do that one first. I'm getting a little bit of a glare. 21 plus the square root of 129. I like to go ahead and enter there, divided by 6. Gives me about 5.4, and it says round your answers to the nearest hundredth, so I need 2 decimal places, so 5.39. Or we got to do 21 minus root 129. 21 minus the square root of 129 divided by 6, enter, gives me 1.61. So that's the x values that will give you the smallest, the largest possible volume. So let's actually plug these in and get dimensions. Those are my x values, those are not my dimensions. So when x is 5.39, it gives us, and I should have left that as exact here. Well, you know what? My bad. Throw that one out. X can't be 5.39. Does everybody understand why? X has to be between 0 and 4. So I could have automatically thrown that out. So now when x is 1.61, I have 8 minus 2 times 1.61. That gives me 4.78. And then 13 minus 2 times 1.61, which gives me 9.78. So the dimensions of the box, and we do need that x value because the x value is right there, 1.61. The box that will maximize volume is We're going to cut 1.61 out of the corner, and it's going to give us a box that is 1.61 by 4.78 by 9.78. It will ask you for the maximum volume. So once, I'm not going to work through it, but in order to find volume, just a reminder, you do length times width times height. Those three numbers you're going to multiply together. That'll give you the box of maximum volume. Okay, on the next one. It says two sides of a triangle, and it does not say right triangle, it does not say acute obtuse. Two sides of a triangle are 12 and 6. The angle between them are theta, or is theta, excuse me. And we're wanting to know, should I make theta really small or really big in order to maximize the area of this triangle? I need to know the theta that's going to give me the biggest possible area here. Now, let me explain one thing. You could plug and play here. You could plug stuff in here, plug and chug, and try to kind of find something out. But again, what if your theta is like 87.36 degrees? You can kind of narrow it down to where it's between 87 and 88, but in order to find the exact, you're going to have to use this process. Okay, so here's something you probably don't remember. How in the world do I find the area of a triangle if I'm given a theta? There's a formula. Let's see. If you've got a triangle, might not, like I said, you might not remember this from pre-cal, but let's say that, again, this is theta and this is A and B. And formulas like this, I'm not going to expect you to memorize. I would give you this formula on the test if you needed it. But now if it was the area of a regular triangle, no, I'm not going to do that. The area of this triangle is 1/2 AB sine theta. So that's an area formula that actually involves two leg lengths and an included angle. 1/2 times this leg times the sine of the included angle. So honestly, this is probably the easiest problem we've worked today. Let's think about our restrictions on theta. I know that theta has to be bigger than 0, because obviously you can't have a triangle if theta is 0. It's going to be a straight little line. And theta, this could be an obtuse triangle, and theta could be huge. So theta could be up to 180, not including 180. It could be 179.9. I don't think that's going to be the right answer, because then you got this really skinny triangle with not much area, and we're trying to maximize area. So, but it could run anywhere between 0 and 180. So that's where you're looking for your maximums here. This is very important in a trig problem. The reason why that is important, because hopefully you remember that if I have something like sine of x equals 1/2, that has millions of answers. I would really like to narrow it down to where there's only one or maybe two answers, not millions. So this is very important that you restrict your domain, that you figure out what values of theta can my problem actually have. So here we go. The area, we need to, in order to maximize area, we need a formula for area. So the first step is to actually write you a little formula. What's the relationship amongst these values? And it's right here. Area is equal to 1/2, and I'm going to plug it in first. 1/2 times 6 times 12 times the sine of, I don't know, theta. That's my variable. That's my changing value. And we clean it up. 1/2 of 12 is 6 times 6 is 36 sine theta. So if I knew what theta was, I could actually plug it in right there, and I've got the area. But I don't. We're changing theta. We're trying to figure out what values of theta would give me smaller or bigger areas. So here we go. We're going to actually find the derivative, and we are finding the derivative with respect to theta, because that's my changing value. That's what we're looking to change here in order to get these different areas. 36 is a coefficient. Bring it down. The derivative of cosine or sine is cosine, and we do not have to use chain rule because it is theta, and it's a clean theta. So here is what we're trying to maximize, or excuse me, here's what we're trying to figure out is equal to 0 or undefined, which will maximize hopefully this function. Like I said, this is probably the easiest one on here. So between 0 and 180, I've got to figure out where's this undefined. Nowhere. It's continuous. It's a cosine curve, or where it's equal to 0. So we come over here and we set it equal to 0, divide by 36. We solve it. Simple trig equation. Where is cosine equal to 0 between 0 and 180? That's only on from here to here. And I know that cosine is equal to 0 at 90 degrees. So I've got a critical value at 90, which actually makes this a right triangle. And it makes it really easy to find the area of. You really don't have to use this formula anymore if you don't want to. But to find the maximum area, it's going to occur at 90 degrees. You can plug it in now. The sine of 90 is 1, correct? And the area would be 36 times 1, which is 36. That's your maximum area. You can try different degree measures, but that's going to be the one that gives you the largest area possible. Okay, here's what the problem says. You've got a right triangle whose hypotenuse is root 15, and it's revolved around one leg in order to generate a cone. So what we're going to do, we're going to take this entire right triangle and we're going to revolve it like this right here around one of these legs. We're going to spin it around, and notice it's going to form a cone. If we trace its path, you now have a cone, which looks, we all know what a cone looks like. To where the height of the cone would be the exact same thing as the height here of this triangle. The radius of the cone would be the same thing as the width here of this. So I'm going to call this H, and we'll call this R. We want to know what H value and R value would maximize the volume here. Let me remind you of something. Use as few of variables as possible. I don't want R's and H's. If there's somehow that we can define R's in terms of H or define H in terms of R's, let's do that. Because right now, here's what we have. Our volume formula, if you don't remember, 1/3 pi r squared, where r is the radius of the base, times the height. The way I told you to remember that in geometry is find the area. If it comes to a point, find the area of the base, multiply it times the height, and then take 1/3 of it. And that's what we've done here. 1/3 of the area of the base times the height. But if at all possible, we want to try to somehow get rid of either an R or an H and just have just R's or just H's. There is a relationship that we can see here between the R's and H's, and it is the Pythagorean theorem. H squared plus R squared equals the square root of 15 squared. You'll see that? That connects H's and R's. So now if I use this, I can somehow get rid of one of these, and it's, watch this, it's actually going to be a little bit easier to get rid of R squared because look, I can move H squared over and say R squared is 15 minus H squared, and instead of solving that again for R, just go ahead and plug it in. There's R squared. Plug this in for it. Makes the problem a little bit simpler. Volume is equal to 1/3 pi. Instead of R squared, I now have 15 minus H squared times H. So since I did have that connection, I could somehow get rid of a variable. If you didn't have this, it would have been impossible. You'd have two different variables. And that's a little bit deeper. Let's clean this up some. Volume is equal to 1/3 pi. Distributive property would be, I'm going to put my h's first, negative h to the third plus 15h. There you go. That's what I'm trying to, that's my volume. Okay, if I've got a height, then I can plug it into that, and I've got my volume. I don't need a radius anymore because, again, I eliminated that variable. I want to maximize this, and again, let's talk about restrictions. H must be greater than 0. And is there, yeah, there's one more. In this right triangle, this is called, again, the hypotenuse. The hypotenuse is always the longest side. So we know that H can't be longer than the longest side, so root 15. It's somewhere on that domain. So look for anything. Is there any values that would restrict domains? That's very important to do first. Okay, since we're trying to maximize, let's find the derivative. I'm going to call it dVdh again. Finding the derivative of the volume with respect to height, because that is our variable here. I want to remind you that anytime you have, this is simply a coefficient. You could distribute out if you want to. I don't really want to. I just want to copy it down. 1/3 pi, and then put you some parentheses. Okay, anytime you have a coefficient, not a constant would be 0, but if you were to multiply this out, this stuff is just being multiplied by this, bring it down. And find the derivative of the rest of it. -3 h squared plus 15. I might actually clean it up a little bit if I did distribute that out, because 1/3 times -3 would be negative pi h squared, and 1/3 times 15 would be plus 5 pi. That'll work. And we want to know where is this derivative, 0 or undefined. It's never undefined. We're good on our interval. It's never undefined. There's no fractions, there's no radicals, there's no tangents, there's no anything that's going to force that to be undefined. So therefore we simply set it equal to 0 and solve it. Because critical values occur, again, I've said this several times, critical values occur anywhere, that's pi, anywhere the derivative is equal to 0. I would reduce this before I started. Divide everything by pi, gives you negative h squared plus 5 equals 0. Looks a little bit better. Subtract 5 gives me negative h squared equals -5. Divide by -1 gives you h squared is 5. So h is equal to the square root of 5. You do not have to worry about plus minus, because again, h is between 0 and root 15. You cannot have an h that's negative. So that's going to be my height that maximizes volume. In order to find the radius that goes along with that, because they're going to ask you for it, just go back here. Because we know that our height, this is where the maximum volume is going to occur. So Pythagorean theorem, you got root 5 squared plus r squared equals the square root of 15 squared. Subtract 5, you get r squared is 10. And we know the radius also is restricted to only positives. So the radius would be root 10. There's 2 of my answers. And then if it asks you for the maximum volume, we can plug the root 5 back in here. And that's going to tell you the volume that's actually going to max.